So Max, as Peter said, he was one of the organizers, and we'll talk about surrogate modeling.
Okay, well, yeah, I'm glad to talk here at this workshop. This talk is going to end abruptly because I abruptly stopped writing at 5 minutes to 10. So, okay, surrogate modeling. So there are several terms on this title slide. So the name of the INI program, as well as the title of the workshop, contains the word pairs and certainly quantifications and complex systems. And the title of my talk contains the word surrogate. So I have to begin by defining these terms for you because there's about, I don't know how many people in the audience, but there's almost that many definitions of each of these words. And mine is probably different than everyone else's. And in fact, I'm not going to even use my definitions. I'm going to use definitions that are narrower than mine. I have to tell you, this talk is unabashedly and unashamedly a talk by a mathematician. So what's a complex system? Well, as I said on the previous talk, this is a term that we invented, at least in the US, to get funding, because it's good to say you're working on complex systems and not on simple systems. So some people think a complex system is one in which there's a daunting and complicated set of mathematical equations from which you can supposedly deduce how the system outputs behave. That doesn't make a complex system in my view. Sometimes the solution of those mathematical equations, even simple mathematical equations, are complex in some nebulous sense, like, for instance, they're chaotic, which is also needs definition. That also doesn't make a complex system in my definition. Being totally befuddled by the equations of how to obtain solution does not make a system complex. That's just weakness on my part. So here's my definition, at least for operating for this talk. A complex system is one for which determining approximate solutions of the mathematical equations is costly. As Peter pointed out, that may take a month to do in some applications, to get one solution, approximate solution. So what's uncertainty quantification? I'm going to have an extremely narrow definition here because I can't talk about everything, or almost I can only talk about very little. So uncertainty quantification is a task of determining statistical information about uncertainty in outputs of a system given statistical information about the inputs. So these are the operating conditions of this talk. What about surrogate? Well, what does the OED have to say? It's a person appointed by authority to act in the place of another, a deputy. In fact, I learned that surrogate was first used in ecclesiastical settings where a bishop would appoint somebody to do some of his job, so he could, I don't know, do what. Second thing is a person, or usually a thing, that acts for or takes the place of another. For instance, I fit the first definition because I'm a surrogate talking instead of someone who really knows what they're talking about. But I'm going to talk about the second one. What the second one doesn't get across is an important connotation the first one that the word deputy has, is that a deputy is someone who is subordinate to the person they replace, has limited powers compared to that person. So that's not really, a substitute doesn't necessarily say that, but so maybe it should say a substitute that is not as good as the original. Anyway, those are my definitions. In practice, you expect to pay a surrogate less to do a job than a person that they substitute for. You also do not expect a surrogate to do as good a job. So in our setting, we expect surrogates to incur less cost, but also to be less accurate. So let's set things up here. So U here is a solution of the PDE, and to confuse you, the half of the audience who are statisticians, my random variable is not x, it's y, and x is my spatial variable. I also have temporal. Now I have an output of interest. Some actually refer to that as the quantity of interest. that depends on the solution of the PDE, like spatial temporal averages of the solution, extremal values of the solution. To keep things simple, I'll assume that G, somehow you process the solution U so that the output of interest doesn't depend on X and T. That just simplifies the presentation. And to me, a quantity of interest is not the output of interest, but is statistical information about the quantity of interest. We rarely, or almost, or never, are really interested in individual realizations of the solution of the PDE. We're interested in statistical information. So let's consider the evaluation of statistical integrals. So I have an integrand f, which depends on G, which depends on U. And f just corresponds to what statistical information you want. If you just want the mean of the output of interest, f is just equal G, and so forth. F is the second moment, G is G squared. And the important thing to remember all throughout that when I write f of y, I really mean the composition of f with G with U, so that f is a function of the random variables. Beginning, you have to solve the PDE to be able to evaluate f. So that makes function evaluations very expensive. Surrogate number one, we're rarely smart enough to be able to exactly evaluate this integral. So we use a quadrature rule to approximate the integral, which is a sum with weights and the integrand evaluated at certain points in the parameter space ym. And often to obtain an accurate approximation of the integral, you need lots of terms in that sum. So m is large in many practical settings. So QOIM, subscript m, is a surrogate for the real QOI. And because m is much bigger than 1, and G depends on f, which depends on the solution U, determining this approximate surrogate for the quantity of interest requires lots of solutions of the PDE. Surrogate number two, we rarely are smart enough, or I am not, to find an exact solution of the PDE. We have to be content with only being able to affect spatial and/or temporal discretizations, and then we find a solution of the PDE, which of the discretized PDE, where J is a number of coefficients or degrees of freedom that you need to determine that you need to find to determine your surrogate Uj for the exact solution of the PDE. And J is very large in some settings. In some settings, it gets so large and things are so complicated it takes a month to find Uj. So Uj being an approximation of U means Uj is a surrogate for U. And because J is a lot bigger than 1, it incurs large computational costs when determining Uj. So because we cannot determine f of y, because we cannot determine U, we have to be content with making a further approximation of the Q of I. So in the sum, we can't put f of ym here. We have to put fj of ym, where fj is a composite function which depends on g, which depends on the surrogate for u. So q of imj is a surrogate of a surrogate, requiring m, a large number m of solutions of a discretized PDE, which is expected to obtain because the number of degrees of freedom. Actually, in practice, we may need to construct a surrogate of a surrogate of a surrogate of a surrogate, because you may not be able to evaluate the G exactly. G, for instance, could be the spatial average of the solution of the surrogate for the solution of the PDE. We may not be able to compute this integral exactly, so that introduces another source of error. And less probable, but possible, you may not even to evaluate f of g exactly. But to keep things from getting completely out of hand, they already are, but could get worse, we will ignore these two possibilities, and we ignore them because they don't really affect what one does about these two large numbers, m and j, which is the numbers we have to deal with to, so I'll only deal with, mostly with j, but a little bit with m. Well, that's not true. We also have to deal with the number n, the number of parameters in our parametrized PDE. That may be large, and I put quotation marks around large because with m and j, large means large. You know, j could be millions, and m could be, you know, hundreds or more. You know, it turns out that n large means 20. So this brings us to the dreaded curse of dimensionality, which is a phrase that we use to refer to the explosive growth in the number of times you have to solve the PDE as the number of parameters increases. So here is a table, number of parameters. M is the number of times a PDE has to be solved by a good method. I'll tell you what these two methods are later on, what goes into these two methods. And you see for 100 parameters, the good method requires 96 plus million PDE solves. The bad method requires more PDE solves than there are electrons in the universe. Much more. Just do a quick calculation. If it takes a month to solve the PDE, how long you have to wait to get the solution of that problem. Anyway, I'll get back to this. So how can one exercise the curse? Well, one can't. You have to accept more modest goals. And remember, we're doubly cursed. The dimension of the spatial approximation is large. That makes each approximate solution of the PDE expensive. And the number of times you have to solve the PDE is large. So not surprisingly, there are two huge armies dealing with these problems. One army is trying to do something about m, the number of PDE solves, and Army B tries to do something about reducing the cost of the PDE solves, or maybe nearly eliminating them altogether. So the rest of the talk is what Army B does. Army A, there's something that of course, not only mathematicians deal with, but this is something statisticians deal with as part of their daily lives. Okay. So what's the goal of surrogate modeling? So those surrogates I talked about at the beginning, I'm not going to talk about at all. So we're starting from scratch. So far I've introduced no surrogates. I'm assuming that I have a surrogate for U built. I mean, I have a UJ solution, a way to solve the PDE. And I even assuming that I've selected a way to approximate the quantity of interest, the statistical integrals. So we want to build a surrogate for the output of interest. You can build a surrogate for the solution itself, but since we're not interested in the solution, it usually pays off to build one directly for the output of interest, or for the integrand, which depends on the output of interest, which depends on the approximate solution. Now, there are good reasons why you should consider both these cases. You say, well, if I'm interested in the quantity of interest, why don't I just do surrogates for F? So let's see a couple of good reasons. Well, one is you may want to have several forms of F. So you may want to compute both the mean and the variance of this output of interest G. In which case you have a choice. You can build a single surrogate for G and use that same surrogate to compute the mean approximations to the mean and the variance. Or you can build two surrogates, one for G and one for G squared, and use that. So it's your choice which one you prefer to do, one or two. Another place where you definitely want to build a surrogate for G and not F is when G is nice, it's smooth, it doesn't have any weird behavior, it has derivatives, but F does not. But F is not nice. So for example, in this kind of risk assessment setting where the statistical information you want is basically the volume of the region when you do the integration where G is bigger than some threshold value. And so F, no matter how smooth and nice G is, F is going to be discontinuous. And building surrogates for discontinuous functions is really hard. And, well, so building surrogates for continuous functions is easy. So this is definitely a case you want to build a surrogate for G, the output of interest, and not the integrand. So let's first talk about classical surrogates. What do I mean by that? We have in mind a class of functions. For example, it could be continuous functions or functions with a certain number of derivatives or square integrable, so forth. So all we know is the functions belong to a certain class. Or we assume so. So we choose a class of surrogates. So there could be Taylor polynomials, there could be interpolating polynomials of total degree, so that the sum of the degrees of the individual terms in multivariable terms is fixed, or tensor products, as which each individual coordinate has a total degree less than some number. Piecewise polynomial, least squares approximations using orthogonal polynomials, for example, or non-polynomial approximations such as radial basis functions, etc. So we choose a class of surrogates. So there's a surrogate building stage, always. There's a few expensive PDE solves are used for a few parameter values to determine the output of interest. So we select some parameter values. That's Army A doing that for us, selecting good parameter values. And then we evaluate our output of interest G at these parameter values. And then we connect the dots. And that's our surrogate. So this looks like an interpolant because it goes through the dots. In which case, how one selects the parameters to build a surrogate is of really extreme importance, as I'll say a little more about in a minute, and impact. Then once you build that curve, then all you have to do, you don't go back to the PDE. Now you need to you need solutions of, you need values of the output of interest at many parameter values to do your statistical integral, to approximate your statistical integral. But instead of going back and solving the PDE at all these zillion parameter points, I just query this curve, this interpolant. So no PDE solves at this stage. So the idea is that the cost of a few solves of the complex system, the PDE, to build the surrogate is amortized over the much smaller costs of evaluating the surrogate many times. So the parameter points should be chosen so they are good for a class of function, for the class of functions that you're, and the class of surrogates you are using. I should have said not only the class of functions, but the class of surrogates. Where good means that you can provide an upper bound for the error that holds for all functions in that class. So let's say you can do that. That's wonderful. Then we're home free. That would be good except for two small problems. For some classical surrogates, there's no more classical surrogate than polynomial interpolation. There's also no greater success in machine learning than polynomial interpolation, although nobody thinks of interpolation as machine learning. We do not know how to choose a good set of points, even in 2D, even with two parameters. It's not really known. I mean, there's certainly no way to get the best, a near best set of points like the Chebyshev points are in 1D. Even in 2D, they're not known analytically. You can compute them, but not analytically. However, so this is polynomial interpolation is really hard in multi-D if you want total degree interpolation. In other words, where the degree of the highest degree is the sum of the degrees of the individual coordinates. If we allow ourselves more build points, which means more expensive function evaluations, we can define good interpolation points. A lot of math people have designed such points, sparse grids, Smolyak points, ta-da. So here's one of them. This is the so-called Smolyak points. So you want to interpolate on a cube, these are good points. You can bound the error interpolation for functions that have sufficient number of derivatives. You might ask, what do you do about these gaps? As Henry asked the first time he saw this picture. Why can we, this is not a space-filling design by any means. And why do we get away with it? It's because of what I said. This works for functions that have a lot of derivatives. So if you have a lot of derivatives, the smoothness of the function will fill in the gaps for you. You don't have to sample everywhere. So sparse grids or Smolyak grids are a judicious sparsification of tensor product grids. So you start out with the grid in all directions that is this fine, and then you throw out zillions and zillions of points to get this. The more points you use, you need more derivatives here than here, or else you're wasting resources to use this one instead of that one. But more points give you better accuracy if you have more derivatives. Okay, another classical surrogate, probably the second most important, is least squares approximation. Having a good set of points is not so important there. The trouble with interpolation is that if you build a bad set of points, you're going to get big oscillations in between the points, and you're going to have a large error. But here we don't go through any of the points, so we can have this smiley curve, and choosing the set of points is not so important. So again, you sample your high-dimensional PDE solver to get approximations to the output of interest, and then you build a surrogate based on these points by minimizing the least squares minimization process. One of the problems is that with least squares, you often have to oversample, and by that you mean that you have to actually get more samples here, more black dots than you would need to uniquely determine a polynomial. But the really bad news for all these classical surrogates is a curse of dimensionality. In fact, that table I showed you, the good method was interpolation on a total degree interpolation. The bad method was interpolation on tensor product grids, where you had complete fill-in of that sparse grid picture. So the degrees of freedom for total degree are bad, the binomial coefficient. For tensor products, they're terrible. It's exponential. And sparse grids are somewhere in between. You're gonna pay. You have to do more samples, so it's somewhere in between. So it's bigger than total degree, but it's still much less than tensor products. What's some more recent developments in surrogate modeling? So for total degree multivariate polynomial of degree p, so remember that means, for instance, if you have a quadratic polynomial in 2D, you have these 6 terms, but you don't have these 3 terms, even though each individual coordinate only has a quadratic power. The sum of the exponents is bigger than 2. So for total degree, so that's a so if your function you're approximating has enough to derivatives, the best total degree polynomial approximation is optimal with respect to convergence rates. So it's optimal in the sense that if you take away points, you're liable to get the convergence rate of a polynomial, the error of a polynomial of 1 degree lower. And if you add more points, your convergence rate is not going to be, your convergence rate is not going to be any better than it is if you use the total degree points. But all of these results assume that the function you're approximating has enough derivatives, but they say nothing about what happens to the specific function you're approximating. For example, if I'm trying to interpolate the function y to the 1,000, well, I can get an exact approximation with only one term, just y to the 1,000. So more generally, you don't need all the terms for a specific function. You may not need all the terms in and this long, these polynomials, as we saw in that table, can get huge in the number of terms. You may not need them all to approximate your function. But you have to use the specific function you're approximating in some way to be able to do that. So mathematicians spending a lot of time these days on a couple of things. The first one is so-called best S-term approximation. Suppose I have a polynomial approximation for f of y, or g of y, it doesn't matter, where you have lots of terms. It's a polynomial, and so we actually start with a polynomial of higher degree than we want. So it doesn't matter, we have a zillion terms. And we're given or choose an integer s, and we only keep the s biggest coefficients in that expansion. This is expansion of it's a polynomial, so each term in the expansion has a coefficient in the sum. And we only keep the s largest terms, and we set all the other terms, we set the coefficient to 0. So this is called an S-term approximation. And if you keep the largest terms, this is what's called the best S-term approximation for the function f. But of course, we cannot really do this in practice, because how do we know which are the largest terms? Well, we only can know which are the largest terms if we compute the whole sum, which we don't want to do. So they're not realizable. However, it's a good thing to know if you could build the S-term approximation, how good is it? How good is it as an approximation? And the reason you want to know this is because if you come up with a different method, you can at least judge how good your method is with respect to this idealized, unrealizable method, which is the best you can possibly do with S terms. And mathematicians spend a lot of time deriving estimates for what the error is in the best S-term approximation. So there's a good handle on what the errors in best term approximations, and you can use that to compare your method with S terms, with only S terms. But because we cannot determine optimal best terms approximation, we are content with using quasi-optimal. And here estimates come about again. So we don't know that we don't want to compute, we don't want to know the coefficients exactly, because that means we have to compute the whole big long thing. But you can estimate the values of the coefficients. Again, without actually solving or constructing this long polynomial approximation, or it doesn't have to be polynomial even. We can estimate through mathematical analysis the values of an estimate for the coefficients. And so instead of using the actual values of the coefficients, which we don't know and don't want to know, we use the coefficient, we keep only the coefficients that the estimates say are probably the biggest. And we'll see why it's probably the biggest, and zero out the rest. So the strategy will be effective only if these estimates are good, and what we like to call sharp. And in particular, if you have estimates for the coefficients from above and from below, what their value is. And by sharp, we mean that the coefficient I'm interested can be bounded from above and below by two numbers, and these two numbers are not far apart. If those two numbers are far apart, in other words, you don't have a sharp estimate, that could lead to throwing out coefficients that you may have that you should have kept if you knew the exact values of the coefficients, or keeping coefficients that you should have been thrown out because you don't really have, because the estimate is not a good surrogate for the exact value of the coefficient. So this is something else mathematicians spend a lot of time on, trying to get sharp estimates for the coefficients of a polynomial for instance, a polynomial approximation. One very important thing to keep in mind, the form of the polynomial has a huge influence on the coefficients. And by form I mean, what polynomial basis do you use? Most people realize, so polynomials can be written as monomials or a sum of hierarchy of orthogonal polynomials, etc., etc. And all of these different cases have been rigorously analyzed and vetted. Okay, let's move to a second thing to try to. So one of the things that's very, very popular these days in our community is to use the idea that comes from signal processing of compressed sensing. So what's the idea here? So what we're going to do is recover the coefficients from an underdetermined system. We're going to solve this matrix. So remember, this matrix is going to have lots of columns, fewer rows. And the idea here is we're going to use some data, that's the left-hand side, and we're going to try to equate, like you would do for interpolation, the data to the sum. You can think of this as this times this as a polynomial evaluated at a particular data point, and this is the data at that point. But it's an underdetermined system, so it's not interpolation. So how did we do this? And the idea here is that if you do this quote unquote right, as indicated here, a lot of these coefficients, when you solve this, when you find a solution of this system, are zero. So you get a sparse solution here, and that means there's a lot of terms in your polynomial that are zero. You've only kept very few terms. So that's the idea of compressed sensing. So sparse signals are recovered by minimizing. So in linear algebra class, how did you learn to solve underdetermined systems? You do least squares. You multiply by you multiply on the inside by A transpose, and you solve a system. You get normal type equations and you solve. So you minimize the least squared error. You try to minimize the L2, little L2 error, least the root mean square error in the solution of this system. I mean, you try to find, the solution that has the smallest L2 norm, little L2 norm. But sparse signals are recovered via so-called sparsity. So when we're going to solve the problem is we're going to find the optimal coefficients by minimizing all possible z's you can put in here. This has many solutions because it's underdetermined. So we're going to minimize the norm of all possible c's that solve this equation. There's a constraint that the equation is solved. But we're not going to minimize the Euclidean norm. We're going to minimize a norm, a little LQ norm with L between 0 and 1. So why does that work? Well, here's a picture. Here are 3 balls, unit balls. This is the circle, which in 2D is, so we assume we have two variables, y1 and y2. So here we have a unit ball in Euclidean space, which is a ball. Here's a little ball in L1, which is a diamond, strictly convex, not strictly convex. And if Q is less than 1, it's not convex at all. So this picture is supposed to tell you that this is my equation AX equals Z. The optimal equation, this is what the optimal, for the optimal coefficient C, this is my equation. And what you read off this is like in the L2 norm, and this is actually the coefficients in that optimal equation. So you see that the L2 norm, unless you have a degenerate linear system where this line would be horizontal or vertical, both coefficients are non-zero. But for the L1 norm or the LQ norm with Q less than a half, one of the coefficients is zero. That's the optimal LQ approximation. So that's why this works. And this was a wonderful invention in signal processing, which is now being adopted over here. So what do? We act like if we were interpolating using polynomials with lots of terms, but with data only given at a few terms. So we have our polynomial here, our zk's are our candidate coefficients, and our phi k is whatever you use to, it doesn't have to be polynomials, by the way, but anyway, let's talk about polynomials. Phi k is just the basis you're using to represent your approximation to f. So, for instance, if you use monomials, it's a bad idea. Orthogonal ideas are better ideas. So z in AZ equals f is just the k vectors of components of my candidate. F is the I vector of data given at evaluating the quantity of interest or the integrand at a data point yi. And A is the IK matrix determined by these terms in the things. And this system is underdetermined. So we can go ahead and solve the optimization problem to find the optimal coefficients. And you're going to find that a lot of them are going to be zero if you do the optimization problem in L1 or LQ with Q less than 1. So there's lots of beautiful theory available. There's even, of course, L2 minimization is wonderful. It's easy. Any other LP minimization is really hard. But, you know, this is something people have now for several years in our community, the PDE community, been working hard at. So there are books written about how to do this. I'm going to close by some recent, and I'm going to talk about reduced order modeling. So very little though, because this is where it ends abruptly. Recent and not so recent developments. So what's a reduced order model? So it's a different tack towards using a few expensive solutions of the PDE to produce a model, a computational model that is much cheaper to evaluate, which we call reduced order modeling. So again, we're going to compute relatively few solutions of the big PDE code, the expensive one, where relative is compared to the large number of solutions that we need to get accurate statistics again. And for time-dependent problems, so we're going to do this for a few parameters, but for time-dependent problems, we also have the opportunity of sampling the solution at several instances of time, although I wouldn't talk about that here. So there are at least two different approaches that use this idea. Usually, they're all reduced basis methods. They're all reduced order methods, but reduced basis method is mostly used in our community where you use all the data you've generated here. You've used all the data you've generated in these few solutions of the expensive PDE as a basis to solve many, many solutions very cheaply. And why it's very cheaply? Because although J is huge, in many, many situations, you can get a reduced basis that's of size 10. Sometimes you have to go to 100 or a few hundred, but it's not millions. And why can you do that? Because these are solutions, these bases are just not arbitrary polynomials that work for a class of functions. These are a basis that explicitly constructed using your PDE. The other approach is like what's the most prominent example is POD. So what you do is, again, you represent your solution, so you solve your phi element system. So you can either represent that as a phi element function, or you can look at the coefficients and express them as a vector. You can do that with any other discretization scheme. So you gather all these solutions as vectors of coefficients. You collect them, those vectors, as columns of a matrix. Then you find the singular value decomposition of that matrix. And the low dimensional basis is defined as, I should say, the left singular vectors corresponding to the dominant singular values. So of course you recognize that POD is equal to PCA is equal to Carhuning-Loewy. Pod has an interesting history which not everyone knows who works in Pod. So, okay. So for both approaches, low dimensional bases are used to find approximate solutions of the PDE for many other parameters, and we get cheap. So traditionally, how do you pick the parameters? So you have to pick parameters in which you solve your expensive PDE. So traditionally, nothing very sophisticated was done about this. So more recently, greedy algorithms, so-called greedy algorithms, have been developed, which is a sequential sampling scheme that follows the following steps. You start with one sample point, perhaps, and you determine a reduced basis of dimension 1, for example, and the corresponding reduced order model, which means the model that's going to solve your PDE just using that one basis function. Then you use some measure of the difference between the solution of the reduced order model and the solution of the expensive model, and you want that measure not to need you to solve the expensive model, so we can discuss that, to determine where in parameter space the reduced order model incurs the greatest error. Then you use that parameter where the greatest error is incurred to go back and solve the expensive model, and then that solution is added to the basis for the reduced order model. And you keep on doing this until you're happy with the basis, whatever that means. And here, now I got to 5 to 10. So that's it for my talk, but I've always been instructed to leave them laughing, so instead of questions, you can read these wonderful quotes about uncertainty quantification. I especially like the last one.
Okay, thanks very much, Mark. I have a quick question, having in mind this is Mr.
Oh, no, Ralph.
Yeah, I don't know if this is quick, and we may want to talk about it afterwards. Can you say a little bit about ties between what you described for surrogate modeling in the context of UQ and what the controls community is looking at? Because you've got a huge background in controls, there's all these synergies, but in many cases I don't think they've been really realized, and POD is certainly one of them. But can you just say a little bit about bringing the two communities, UQ and controls, closer?
Control community.
Yeah.
Control, yeah.
Well, we need another program at the INI, I guess. But no, well, yeah, like you said, there's huge overlap. Pod is very prominent in both, and in fact, a lot of the stuff that's done in UQ, the control community did it first, and so they've adopted Pod because people who knew about Pod did it.
Pod keeps getting reinvented every
Yes, exactly right.
number of years.
I haven't seen, well, I don't know, I haven't seen some of these other ideas that are using UQ, like compressed sensing, used that much in the control community. So yeah, I think there should be some backfeed to control. I agree.
It's a little bit like lasso that's used in the statistical community. All right, one quick one, yes.
Yeah, actually I have two quick ones. So basically, you use a parametric model or your surrogate model to basically approximate a continuous function with a discrete finite dimensional function. And then you use your basis functions, like you said, polynomials. Polynomials in practice show sometimes very weird behavior, so I was wondering whether people use maybe bounded functions with bounded derivatives, such as piecewise linear functions.
Oh yeah, absolutely. Yeah.
Errors.
Yeah, especially people like me who come from the phi element community love piecewise polynomial functions. Yeah.
And the second question is, basically you do this to avoid or to circumvent the curse of dimensionality. But basically, to make your parametric model a good fit, you have to increase the basis. And even though you can use like complete set of polynomials rather than the tensor product, still when fitting the model, it's not completely free of the curse of
No,
dimensionality.
no, not at all, yeah. And I did not mention a single word about a big industry, which is, well, it's been a huge industry in statistics forever, and it's recent with us of trying to figure out which are the unimportant parameters.
All right, that's very nice. Thanks very much.